This video discusses how to evaluate annotation quality. I'll cover inter-annotator agreement, focusing specifically on Cohens kappa. I'll work through a case example of computing Cohens kappa for a small set of annotations, and then briefly talk about interpreting kappa values and adjudicating disagreed upon instances to create your gold standard set of labels. This video is the last video in a series of videos covering the data collection pipeline from start to finish. If you haven't watched the first 4 videos, you may want to watch them before proceeding. This video focuses specifically on evaluating annotation quality after you've collected your annotations. Evaluating annotation quality is very important because it allows you to objectively justify the contributions of your dataset. Demonstrating that your annotations are high quality will make other people much more likely to adopt your dataset for training their own models. And for your own sake, it'll be a good indicator of how easy or challenging a task is for humans, which can help establish an upper performance bound. Most people evaluate annotation quality by computing some measure of inter-annotator agreement, and having inter-annotator agreement scores will almost certainly be necessary if you intend to publish an article about your dataset in a peer-reviewed venue. Inter-annotator agreement scores tell you how similarly multiple annotators labeled the same set of data instances. If they exhibit high agreement, that means that your task is easily learnable given proper guidelines and training, and should in turn, at least in theory, be learnable by automated models as well. It also means that if a third-party researcher were to solicit annotations for the same task, they would likely end up with the same labels for the instances in the dataset. If, on the other hand, you find low inter-annotator agreement scores, it can mean that your guidelines were too confusing or that perhaps the task is too subjective to be reasonably automated. To compute inter-annotator agreement, you need to collect labels from 2 or more annotators for the same set of data instances. If you use 2 annotators, you can say that the data is double annotated. If you use 3 annotators, you can say that the data is triple annotated, and so forth. The number of annotators you choose to use will depend largely on the resources that you have available. If you're using crowdsourced annotations, you may want to solicit more annotations per instance than if you're using expert annotators, since annotations from crowd workers can often be less reliable at an individual level. There are numerous formulas that researchers use for computing inter-annotator agreement. Sometimes you'll see people compute simple percent agreement. This is just the percentage of instances that a pair of annotators agreed upon from among all instances. Percent agreement isn't the most useful metric though because it doesn't take into account random chance agreement. More commonly, you'll see people compute kappa, and often a specific form of kappa called Cohens kappa, as well as Krippendorff's alpha. Cohens kappa is generally the default inter-annotator agreement metric used when you have all data instances annotated by 2 specific annotators, and it's the primary metric we'll work through in this video. Specifically, Cohens kappa measures the agreement between 2 annotators while considering the possibility of chance agreement, using the formula shown here, where P sub r is the observed agreement, and P sub e is the expected agreement if annotations were randomly assigned. To show how it works more concretely, we can work through the case example here. Let's say we have a dataset of 4 movie reviews, and we've collected sentiment labels for each of those movie reviews from 2 annotators. So for each instance, annotators A and B each indicated whether the review expressed positive, negative, or neutral sentiment. We can go ahead and visualize the annotations in a table, much like a confusion matrix that you'd use to compute precision recall in F1 for a machine learning classifier, where we have annotator A on the y-axis and annotator B on the x-axis. We fill in the table with what we see from the annotations we collected. So there was one case where both annotator A and annotator B marked an instance as positive, one case where annotator A marked an instance as positive, but annotator B marked it as neutral, one case where annotator A marked an instance as neutral, but annotator B marked it as negative, and one case where both annotator A and annotator B marked an instance as negative. This means that the actual observed agreement probability was 2 out of a total of 4 cases, or 0.5. Now, we need to compute the expected chance agreement probability. We see that annotator A assigned the positive label twice, so half of the time, and annotator B assigned the positive label once, so 25% of the time. This means that if we added a new instance, there'd be a 50% chance that annotator A would assign it a label of positive, and a 25% chance that annotator B would assign it a label of positive. So there'd be a 0.125 chance that they'd both assign a positive label by chance. Following the same logic, there'd be a 0.0625 chance that they'd both assign a label of neutral by chance. And there'd be a 0.125% chance that they'd both assign a label of negative by chance. We can find our overall expected chance agreement probability by summing up those individual probabilities for an expected chance agreement of 0.3125. This means that for computing kappa, our numerator will be 0.5, that's our observed agreement, minus 0.3125. Our denominator will be 1 minus 0.3125. This will give us 0.1875 over 0.6875 for a kappa of 0.27. Although Cohen's kappa is very common, it's not the only sophisticated way to compute inter-annotator agreement, as already mentioned. In cases when each instance was annotated by more than 2 annotators, you could compute Cohen's kappa between each possible pair and then average those scores. But you could also compute Fleiss's kappa or Krippendorff's alpha. Fleiss's kappa is a slightly modified equation in which you're subtracting the average of the percentages of annotators expected to agree by chance from the average of the percentage of annotators who were observed to agree. So this is useful because it allows the annotators themselves to vary across instances. Annotators A, B, and C may have labeled instance 1, whereas annotators A, C, and D may have labeled instance 2, and so on. Krippendorff's alpha allows for the same thing, but sets the equation up slightly differently, basically computing a ratio between observed and expected disagreement. It has the additional advantage of being able to handle missing data, but it's much more computationally expensive to compute. Once you've computed your inter-annotator agreement, you'll need to interpret the score you computed to make your objective assessment of annotation quality. There's some disagreement, no pun intended, about what a good kappa score is, but in general, most researchers adhere to the scale you see here. So a kappa of less than 0 indicates poor agreement, essentially less than chance. A kappa between 0 and 0.2 indicates slight agreement. Between 0.2 and 0.4 indicates fair agreement. Between 0.4 and 0.6 indicates moderate agreement. Between 0.6 and 0.8 indicates substantial agreement. And greater than 0.8 indicates perfect agreement. You should in most cases aim for a kappa between 0.6 to 0.8 to confidently be able to justify your annotation quality. It's pretty rare to achieve a kappa higher than 0.8 for most tasks. For some tasks, a kappa between 0.4 to 0.6 can be considered reasonable, but it'll be more difficult to justify to peer reviewers. If your kappa falls below 0.4, you should reconsider your annotation schema and see if there are ways to make your annotation task clearer or more straightforward to annotators. Once you're satisfied with your inter-annotator agreement scores, you'll need to select your final gold standard labels that you'll use for the instances in your data set. For instances the annotators agreed upon, this is easy. You just use that label directly. However, unless you had absolutely perfect agreement, you'll need to come up with some way to adjudicate the instances that annotators disagreed about. One way to do this, if you have access to a task expert who wasn't already involved in annotating the data, is you can pass along the instances to that person, and they can make an informed judgment to assign the gold standard label based on all of the information available. If you don't have a third-party adjudicator, you can instead average the annotations if they're real-valued numbers, or take the majority vote if they're categorical labels. Make sure that you don't leave adjudication as an afterthought. High-quality adjudication can take time, especially if you're using an expert adjudicator. If you find yourself in the role of the adjudicator for your task, which should only happen if you didn't annotate any of the data yourself, you should carefully consider the annotations provided by your annotators, as well as the overall instance context. Don't feel pressured to just choose the majority because it's possible that some agreements may have occurred due to random chance, but also don't disregard the annotator's suggestions entirely unless you have a justifiable reason for doing so. If you recruit multiple adjudicators for your task, you should compute their inter-annotator agreement on a sample of overlapping adjudications to make sure they're on the right track and not making drastically different decisions from one another. Finally, after your data has been adjudicated, your corpus is finally complete. Make sure to document the entire data collection process while it's still fresh in your mind, and if you plan to publish the corpus, make sure the data is easily accessible for other researchers. You might want to ask a friend who's completely unfamiliar with the project to try downloading and using the dataset and see how easy it is to use. You can now use your dataset to advance your progress towards your project goals.